Imagine for a moment that you're in the cockpit of an aircraft that weighs over 7 tons when fully loaded. The engine in front of you is so massive that it nearly blocks your view of the horizon. You're at an altitude of 10,000 meters, where the air is so thin that a human being without proper equipment would lose consciousness in seconds. And then you push the stick forward and plunge toward the ground at speeds approaching the sound barrier. This is no fantasy. This was the daily life of the pilots who flew the Republic P-47 Thunderbolt during World War II, a machine that defied all conventions of aircraft design at the time. The P-47 Thunderbolt wasn't just another fighter. It was a flying paradox, a mechanical contradiction that shouldn't work in theory, but in practice became one of the most important and effective aircraft in the most devastating conflict in human history. When you look at photographs of this aircraft, the first impression is one of sheer brutality. There's no subtle elegance here, no smooth, seductive lines like a British Spitfire or the aerodynamic aggression of a Mustang. The Thunderbolt was different. It was bulky, heavy, imposing. It looked more like a tank with wings than a traditional fighter. And it's precisely this appearance that leads us to the central question. Why did the engineers at Republic Aviation Corporation make such radical, seemingly illogical decisions when designing this aircraft? But before we dive into this incredible story, if you're enjoying this content, don't forget to subscribe to the channel and leave a comment with the time you watch this video. This really helps the channel grow and continue bringing you fascinating stories like this one. To truly understand the insanity of the P-47's engineering, we need to travel back in time to the late 1930s when the world teetered on the brink of an abyss. Europe was already in flames, and the United States, though officially neutral, watched with growing concern as German forces relentlessly advanced across the continent. Reports from the Battle of France and later the Battle of Britain offered stark lessons about what worked and what didn't in modern aerial combat. Alexander Kartveli was Republic Aviation's chief engineer, a Georgian immigrant who had studied in France and possessed a brilliant and unconventional mind. Kartveli wasn't one to follow the obvious path. He approached problems from angles other engineers wouldn't even consider. And when he sat down to design what would eventually become the P-47, he faced a series of seemingly insurmountable challenges. The American military wanted speed. They wanted range. They wanted weapons payload. They wanted ruggedness. They wanted high operating altitude. And they wanted all of this in a single package. Now, any experienced aeronautical engineer will tell you that aircraft design is an endless series of compromises. You want speed? You sacrifice maneuverability. You want range? You add fuel weight. You want heavy weapons? There goes your power-to-weight ratio. It's like trying to solve a Rubik's Cube, where every move affects every other face simultaneously. But Kartveli had a vision, and that vision began with a decision that would make other engineers shake their heads in disbelief. He would choose the most powerful engine available, no matter how large, heavy, or complex. The choice fell on the Pratt & Whitney R2800 Double Wasp, an 18-cylinder radial engine arranged in 2 rows that produced an incredible 2,000 horsepower. To put that in perspective, this engine alone weighed over a ton. It was an absolute masterpiece of mechanical engineering, with 36 valves, dual ignition, and a cooling system that had to move enormous amounts of air through its fins to prevent the metal from literally melting under operating load. Now, radial engines were nothing new in aviation. In fact, they were quite common in aircraft of the time, especially bombers and transports. But using such a massive radial engine in a high-performance fighter was considered problematic for several reasons. First, radial engines have a huge frontal area. They are cylinders arranged in a circle, which means you're essentially putting a metal wall in front of your aircraft. This creates tremendous aerodynamic drag, and drag is the mortal enemy of speed and efficiency. The Germans had solved this problem by using inline engines with cylinders arranged in a line or V like in an automobile. This allowed for a narrow aerodynamic nose, as seen in the Messerschmitt Bf 109. The British did the same with their Spitfires and Merlin engines, but Kartveli had his reasons for going against the grain. Radial engines were robust. They could sustain severe damage and still function. One cylinder could be completely destroyed by enemy fire, and the other 17 would continue pushing the aircraft home. Furthermore, Radial engines had simpler cooling systems. They didn't require vulnerable and heavy liquid radiators with their complex piping that could be punctured by a single projectile. But there was a huge problem to solve. How do you fit a gigantic radial engine into a fighter and still maintain the aerodynamics necessary for high speed? Kartveli's answer was simultaneously elegant and completely insane in its complexity: turbocharging. This is where the P-47's engineering truly begins to show its absolutely mad genius. Let's understand what a turbocharger is and why it was so revolutionary in this context. As an aircraft climbs, the air becomes increasingly thinner. Fewer oxygen molecules are available for combustion in the engine. This means that the higher you fly, the less power your engine produces. At extreme altitudes, a normally aspirated engine loses most of its power. A turbocharger solves this by taking the hot, high-energy exhaust gases that would normally simply be wasted and using them to spin a turbine. This turbine is connected to a compressor that forces more air into the engine, compensating for the altitude and maintaining power. But here's where it gets tricky, where the engineering becomes truly daunting in its complexity. The P-47's turbocharger wasn't a small auxiliary unit hidden in some compartment. It was a General Electric monster, weighing hundreds of pounds. And it couldn't be installed near the engine in the forward fuselage because there simply wasn't room. So Kartveli had to place the turbocharger in the rear of the fuselage, just below the vertical empennage. Think about what this means in practical terms. Air needs to flow from the intake at the front of the aircraft, past the engine at the front, and then somehow reach the turbocharger at the rear. But that's not all. The extremely hot exhaust gases from the engine also need to be channeled to the rear to drive the compressor turbine. And then, the compressed air needs to return from the rear to the engine at the front. All of this needs to happen through ducts, pipes, and passages that must be designed to minimize pressure losses, withstand extreme temperatures, and still not add unnecessary weight to the structure. The result was a duct system that looked more like the inside of an oil refinery than a fighter jet. Pipes were everywhere, running over, under, and around the fuel tanks, the control systems, and the cockpit. If you've ever seen photographs of the P-47 with the panels removed, you'll understand what I mean. It seems impossible that all of that could fit inside that fuselage. It looks like an organized mess of engineering that violates all the rules of simplicity and elegance we normally associate with good design. But it worked. My God, it worked. The turbocharging system allowed the P-47 to maintain maximum power at altitudes where other fighters were already suffocating. The official operational ceiling was about 40,000 feet, but there are reports of P-47s actually operating much higher. This gave American pilots a tremendous tactical advantage. They could choose when and where to fight. They could hover above the enemy, wait for the right moment to strike, and then dive in with all that mass and all that power. And here we come to another absolutely insane characteristic of the P-47, its weight. With all the systems we've mentioned, the massive engine, the turbocharger, and all the associated piping, the fuel tanks, and the armament we'll discuss later, the P-47 weighed about 4.5 tons empty. Fully loaded for a combat mission, it could easily exceed 7 tons. To put this in perspective, the British Spitfire, considered one of the best fighters of the war, weighed less than half that when fully loaded. Pilots who flew both the P-47 and other aircraft of the era often described the first time they climbed into a Thunderbolt as a surreal experience. You didn't enter the cockpit. You climbed up to it, using a series of steps built into the wing. Once inside, you sat quite high, which was good for visibility, but also meant you were very far from the ground during takeoff and landing, requiring precise judgment. And when you fired up that monstrous engine and began taxiing, you immediately felt like you were in command of something very different. Takeoff was a unique experience. You needed a long, very long runway. With all that weight, the P-47 didn't leap off the ground like a light, agile fighter. It accelerated and accelerated. You pushed the throttles all the way forward. The engine roared with a sound you could feel in your bones, and the aircraft gradually, almost reluctantly, lifted off the ground. Once airborne, you needed to gain speed before attempting any maneuvers. Attempting to climb too early or too aggressively with too little speed was an invitation to disaster. But once at altitude, once it had the proper speed, the P-47 transformed. That weight that seemed like a curse on the ground became a tactical advantage in the sky. In a dive, the Thunderbolt was absolutely devastating. The combination of weight and power meant it could accelerate out of a dive like few other fighters. There were reports of pilots reaching speeds approaching 500 miles per hour in vertical dives. At these speeds, the P-47 began to encounter the effects of air compressibility, phenomena that would only be fully understood later with the advent of supersonic aviation. The controls became heavy at high speeds. The aircraft began to vibrate. Some pilots reported difficulty pulling the aircraft out of a dive because the aerodynamic forces were so intense. But this diving ability was also a combat and escape tactic. If a P-47 pilot found himself in trouble, he could simply push the nose down and dive. Few enemy fighters could keep up, and attempting to follow was extremely dangerous because their lighter airframes were not designed for such extreme speeds. Now let's talk about the armament, because here the P-47's design philosophy reaches another level of glorious excess. Most fighters of the era carried between 4 and 6 machine guns. The P-47 carried 8, and these weren't small machine guns. They were 50 caliber Browning M2s, the same weapons you'd find mounted on jeeps, tanks, and fortifications. These were weapons designed to destroy light armored vehicles and aircraft with equal effectiveness. Each weighed about 30 kilograms and fired projectiles the size of your index finger at a muzzle velocity of nearly 300 feet per second. 4 machine guns were mounted on each wing, for a total of 8 weapons. When a pilot pulled the trigger, all 8 weapons fired simultaneously, creating a terrifying cone of fire. The combined rate of fire was about 5,000 rounds per minute. Imagine 5,000 large-caliber shells being launched toward the target every 60 seconds. The total ammunition carried was about 3,400 rounds, giving the pilot approximately 40 seconds of total firing time if he held the trigger down continuously. Of course, no pilot did that. They were trained to fire in short, precise bursts, but the point was, when you needed to destroy something, you had more than enough firepower. A single second of concentrated fire from all 8 machine guns could literally disintegrate an enemy fighter. The fuselage could be cut in half. Wings could be ripped off. Engines could be turned into smoking scrap. But there was a price to pay for all this firepower. First, there was the weight. 8 heavy machine guns plus 3,400 rounds added well over half a ton to the aircraft's weight. Second, there was the recoil. When all 8 guns fired, the recoil force was substantial. Pilots reported feeling the aircraft slow slightly when they opened fire. The entire fuselage vibrated with the mechanical roar of the guns. Empty shell casings were ejected from the wings in a golden shower that fell to the earth thousands of meters below. And then there was the question of where to put all this weaponry. The P-47's wings needed to be strong enough not only to support the weight of the weapons and ammunition, but also to handle the aerodynamic forces during violent combat maneuvers. Kartveli and his team designed a wing structure that was a masterpiece of structural engineering. It used multiple spars, reinforced ribs, and relatively thick aluminum skin. The result was an incredibly strong wing, capable of withstanding load factors that would destroy lighter fighters. This structural robustness became one of the P-47's defining characteristics. Pilots quickly discovered that the aircraft could sustain absolutely brutal combat damage and still fly. There were documented cases of P-47s returning to base with massive holes in their wings, entire sections of skin ripped off, and control systems partially destroyed. Yet the pilots managed to land safely. This survivability was invaluable. Every pilot who returned alive was a pilot who could fly again tomorrow, who could gain experience, who could train others. The fuselage was also built like a tank. The cockpit was surrounded by armor plates that collectively weighed over 100 kilograms. There was an armor plate behind the pilot's seat, armor plates protecting the engine from fire from behind, and even the front windshield was made of thick, armored glass. All of this added weight, of course, but it also meant that a pilot had a reasonable chance of survival, even if his plane was hit repeatedly. The fuel tanks were self-sealing, a relatively new technology at the time. If a tank was punctured by enemy fire, a special rubber compound would automatically expand and seal the hole, minimizing fuel loss and, more importantly, drastically reducing the risk of fire. In-flight fires were a leading cause of pilot deaths in World War II. A punctured fuel tank that leaked inside the fuselage could create flammable vapors that could explode with the slightest spark. Self-sealing tanks weren't perfect, but they saved countless lives. Now, with all that weight, all that armor, and all that firepower, you might be wondering about maneuverability. And that's a fair question, because here we enter one of the great debates among pilots and historians. Was the P-47 a good dogfighter, a good close-in, rotating air combat fighter? The short answer is not exactly. The long answer is more complex and tells us a lot about aerial tactics and how to use the aircraft's strengths and weaknesses. In low-speed, low-altitude dogfights, where the fight came down to who could make the tightest turns, the P-47 was at a disadvantage. Lighter fighters like the Japanese Zero, or even the Messerschmitt Bf-109, could outperform the Thunderbolt in sustained turns. They had a smaller turn radius, could bleed less energy in maneuvers, and could turn their noses toward you more quickly. Trying to fight in these conditions against a skilled opponent in an agile aircraft was asking for a kill, but P-47 pilots quickly learned not to fight this way. They used their aircraft's advantages. They fought vertically rather than horizontally. They used speed rather than agility. The typical tactic was to use superior altitude to dive down at high speed, deliver a devastating fire pass with those 8 machine guns, and then use the energy of the dive and engine power to quickly climb back to a safe altitude. This was the boom and zoom tactic, and the P-47 was absolutely perfect for it. If the enemy attempted to continue climbing, it lost speed much faster than the Thunderbolt. And at lower speeds and higher altitudes, the P-47, with its turbocharger, still had power left while the enemy's engine was choking. This reversed the advantage. Suddenly, it was the P-47 pilot who had superior power, who could dictate the terms of the fight. He could choose to attack again or simply walk away. And if the P-47 pilot decided to dive away again, there was nothing the enemy could do but watch. This understanding of proper tactics didn't come immediately. There were losses early on when inexperienced pilots tried to fight the P-47 the same way they would a more traditional fighter. But once the correct tactics were developed and disseminated, the P-47 became an extremely effective platform. Experienced pilots loved the aircraft. They trusted it. They knew it would bring them home. And then came the evolution of the P-47's role, a transformation no one had fully anticipated, but which would make the aircraft even more valuable. As the war progressed, as the Allies began to advance first in the Mediterranean, then in France, fighters needed to do more than just fight other fighters. They needed to attack ground targets. They needed to support troops on the ground. They needed to destroy trains, trucks, tanks, bridges, anything that kept the enemy going. And here the P-47's seemingly excessive design revealed its genius. That weight, which was a problem in dogfighting, was actually an advantage in ground attacks. A heavy aircraft was more stable as a firing platform. It wasn't tossed sideways by low-altitude turbulence or nearby anti-aircraft fire. That robust structure? It meant the P-47 could absorb heavy ground fire that would destroy lighter fighters. Those 8 50-point machine guns, they were absolutely devastating against ground targets. Furthermore, the P-47 could carry additional weapons under the wings. Bomb pylons could be installed, allowing the aircraft to carry up to 1,000 kilograms of ordnance. This could be conventional high-explosive bombs, incendiaries, external fuel tanks to extend range, or perhaps most terrifyingly, rockets. High-velocity rockets were terrifying weapons, not very accurate but devastating when they hit, capable of destroying even heavy tanks with a single direct hit. P-47 pilots developed elaborate ground attack tactics. They flew in coordinated formations, attacking from different angles to overwhelm anti-aircraft defenses, and used topography to mask their approach. A column of German vehicles advancing along a rural road in France could suddenly find itself under attack by a dozen Thunderbolts. The sound was deafening, the roar of engines amplified by the Doppler effect as the aircraft dove. Then came the crackle of machine guns, the whistle of rockets, the explosions of bombs. In a matter of minutes, an entire column could be turned into a smoking wreck. This type of close-in air raid had a tremendous psychological impact on the German forces. Veteran soldiers who had faced heavy bombing, artillery, and tanks said that fighter-bomber attacks were the worst. There was no warning. There was nowhere to hide. You were simply there doing your job, and then death fell from the sky in a fury of metal and fire. Morale plummeted. Troops became reluctant to move during the day. Logistics, already tense for the Germans, became nearly impossible. The numbers tell the story. During the Western European campaign of 1944-1945, P-47s destroyed thousands of locomotives, tens of thousands of railroad cars, countless trucks, and armored vehicles. They attacked airfields, destroying German aircraft on the ground. They cut communication lines, destroying bridges and railway facilities. They did this while still fulfilling their original role as air superiority fighters, escorting bombers and engaging enemy interceptors. This versatility was no accident. It was the direct result of those design decisions that seemed so excessive, so insane on paper. Kartveli had built an aircraft with enormous safety margins. There was power to spare. There was structural capacity to spare. There were redundant systems. This meant the aircraft could be adapted, modified, and used in ways never originally envisioned. Different variants of the P-47 were produced throughout the war, each refining the basic design. Later versions had greater range with larger fuel tanks. Some versions had glass bubble cockpits that provided 360-degree visibility. Engines were improved, producing even more power. By the end of the war, there were versions of the P-47 that were significantly more capable than the initial models, but all shared the same fundamental design philosophy. Build strong, build powerful, make no compromises. But all this capability came at a cost, and I'm not just talking about weight. P-47s were complex to maintain. That revolutionary turbocharging system, it was also a constant source of headaches for maintenance crews. Oil leaks were common. Ducts could crack under thermal stress. Engines could fail if operated incorrectly. Each aircraft required hours of maintenance for every hour of flight time, far more than simpler fighters. And then there was the financial cost. Each P-47 cost approximately $100,000 to produce, a fortune at the time. That was more than twice the cost of a P-51 Mustang, another famous American aircraft. But the military kept ordering more and more Thunderbolts because they worked, because they brought pilots home, because they won battles. Production eventually reached staggering levels. At its peak, Republic Aviation and its subcontractors were churning out P-47s at a rate of over 700 per month. Factories operated around the clock. Tens of thousands of workers, many of them women who had taken the jobs of men who had gone to war, painstakingly assembled these complex machines. It was a feat of industrial engineering as impressive as the aircraft's design itself. In total, over 15,000 P-47s were built, making them one of the most produced fighters of World War II. They served not only with the United States, but also with several allies. The British RAF used Thunderbolts, primarily in the Southeast Asian theater. The Free French received P-47s, even the Soviet Union, which generally preferred to use its own designs, received some Thunderbolts through the Lend-Lease program, though they were not particularly popular with Soviet pilots, who preferred their nimble Yaks and Lavochkins. But it was in the European and Pacific theaters, with American forces, that the P-47 truly proved its worth. Aces were made flying Thunderbolts. Robert Johnson, one of the greatest American aces of the war with 28 confirmed victories, flew almost exclusively P-47s. He was famous for saying that the P-47 could take any kind of punishment and keep flying. And he had personal experience to back up this assertion, having brought his aircraft back on multiple occasions with such severe damage that maintenance crews were amazed he had managed to land it. Francis Gabreski, another famous ace with over 30 victories, was also a devotee of the P-47. He deeply understood how to utilize the aircraft's unique characteristics. He preached tactical discipline. Never fight in the enemy's strong point. Always use your own advantages. Maintain speed. Maintain altitude. Choose your moments. These lessons were learned through bloodshed and passed on through countless briefings and debriefings. In the Pacific Theater, where the P-47 arrived later in the war, it faced a different set of challenges. Japanese fighters, especially the Zero, were extraordinarily agile at low speeds. They were light, simple, and deadly in a circle. But the P-47 had the same advantages it had in Europe: speed, altitude, firepower, robustness. pilots applied the same tactics with the same success. Furthermore, in the Pacific, with its vast ocean distances and dense jungle, the P-47's ruggedness was even more valuable. Forcing an emergency landing in Europe was dangerous, but there was a reasonable chance of being rescued or captured. In the Pacific, an emergency landing in the ocean or jungle often meant death by drowning, exposure, or hostile enemies. So an aircraft that could bring you back even when severely damaged was literally the difference between life and death. But let's talk about something that's often overlooked when discussing military aircraft. What was it really like to fly a P-47? What was the human experience like? Not just the numbers and specifications. We have pilot accounts, diaries, and interviews from decades later, and they paint a vivid picture. First, the noise. You can't truly understand it until you've experienced it. But imagine sitting just a few feet from a 2,000 horsepower engine without adequate sound insulation. The roar was constant, piercing, felt as much as heard. Pilots wore thickly padded leather helmets, but even so, many suffered permanent hearing damage. For hours on end, this noise was your constant companion, a physical reminder of the raw power that kept you aloft. Then there was the vibration. The radial engine, by its nature, wasn't perfectly balanced. There was a constant pulsation you felt through every control surface, through the stick, through the rudder pedals. It wasn't necessarily uncomfortable, but it was omnipresent. You learned to sense the engine's health through these vibrations. Subtle changes could indicate problems before any instruments showed anything amiss. Cold was another constant factor at high altitude. At 10 or 12,000 meters, the outside temperature could easily be 50 degrees below zero. Even with electrically heated flight suits, pilots froze. Their fingers went numb. Their feet lost sensation. Breathing through oxygen masks was uncomfortable, the dry air irritating the lungs. Missions lasting 3, 4, or 5 hours were exercises in physical as well as mental endurance. And then there was the fear. No matter how well trained you were, no matter how many missions you flew, there was always fear. Fear of mechanical failure, fear of anti-aircraft fire, fear of enemy fighters, fear of making a mistake. Pilots dealt with this in different ways. Some developed elaborate rituals before each mission. Others became superstitious, wearing the same pair of socks, carrying the same talismans. Some repressed it completely, building emotional walls that would only crumble years after the war. But there were also moments of pure exaltation. There's something fundamentally human about flying, about defying gravity, about having the entire world spread out beneath you like a living map. And in a P-47 with all that power at your command, there were moments when you felt not just powerful, but invincible. Rolling the aircraft, feeling the response of the controls, pushing the throttles forward, and feeling the acceleration pushing you back into the seat. These were visceral experiences that stayed with pilots for the rest of their lives. The stories that have survived are remarkable. There is the account of a pilot whose P-47 was hit by anti-aircraft fire over Germany. The shell passed straight through the wing, leaving a hole the size of a dinner plate. He managed to fly 200 miles back through enemy territory and land safely. There is the story of another pilot who collided mid-air with a German Focke-Wulf during a dogfight. The P-47's propeller literally severed the enemy fighter's tail. His own plane suffered extensive engine and fuselage damage, but he managed to glide to Allied territory and make a forced landing in a field. These were not rare exceptions. There are hundreds, perhaps thousands of similar stories in the archives. They testify not only to the skill and courage of the pilots, but fundamentally to the absolute robustness of the machine they flew. Kartveli and his team had built something that could withstand abuse, that would break other planes and still function. But the P-47's engineering wasn't just about making something strong and powerful. There were also subtle refinements, small touches that demonstrated careful attention to the pilot's experience. The cockpit, for example, was relatively spacious for a fighter of the time. There was room to move around, to adjust during long missions. Visibility, especially in later versions with the bubble canopy, was excellent. The controls were logically arranged. Critical instruments were where you'd expect them to be. The hydraulic system that operated the landing gear, flaps, and other systems was robust and reliable. This may not sound exciting, but consider what it means. A landing gear that doesn't lower means a belly landing that will likely destroy the aircraft and potentially kill the pilot. Flaps that don't work mean much higher landing speeds and a greater chance of an accident. These systems needed to work every time, under all conditions, even after the aircraft had been hit by enemy fire. The electrical system was similarly oversized, with multiple generators and backup batteries. Radios had redundancy. Even small details like instrument panel lighting for night flying were carefully considered. It all added up to a professional, reliable aircraft that allowed the pilot to focus on the mission rather than fighting the machine. As the war progressed and more P-47s were built, manufacturing also evolved. Early aircraft were essentially hand-built, with extensive individual measuring and adjustment. But as production increased, processes were standardized. Jigs and fixtures ensured interchangeability of parts. Assembly line techniques, adapted from the automotive industry, were applied. This not only sped up production, but also improved consistent quality. And then there was the logistical support. An aircraft as complex as the P-47 required an elaborate supply chain. Spare parts had to be available wherever the aircraft operated, from bases in England to remote islands in the Pacific. Mechanics needed to be trained not only in basic procedures, but also in complex troubleshooting. Technical manuals ran to thousands of pages, covering every system, every component, every possible procedure. Republic Aviation established training schools, sent technical representatives into the field, and published regular bulletins on problems and solutions. This kind of comprehensive support was critical to keeping fleets operational. There was no point in having thousands of P-47s if half of them were on the ground waiting for a part or someone who knew how to fix them as the war drew to a close in Europe in May 1945 and then in the Pacific in August. P-47 production began to slow. The transition to peacetime meant the desperate need for combat fighters had passed. Many P-47s were simply scrapped, cut up and melted down for metal. Others were sold to allies or stored for possible future use. But the P-47 continued to serve for years after World War II. During the Korean War in the 1950s, although jet aircraft were now the norm for air-to-air combat, P-47 still saw limited use in ground attack roles in some theaters. Several South American nations operated P-47s throughout the 1950s and even into the 1960s. For these countries with limited military budgets, the Thunderbolt still offered impressive capability at a relatively low cost. The P-47's legacy in aviation history is complex and multifaceted. In purely technical terms, it represented the pinnacle of a certain type of design philosophy. It embodied the idea that more is more, that limitations can be overcome through sheer power and robustness. This approach had obvious drawbacks in terms of weight, complexity, and cost, but it also had tremendous advantages in terms of capability and survivability. Compared to its contemporary and eventual rival, the P-51 Mustang, the P-47 was less elegant, less efficient in terms of range per fuel burn, and less agile. But it was more robust, carried more armament, and could absorb more punishment. There were passionate debates among pilots about which was the superior aircraft, and the honest truth is that there was no simple answer. They were different tools for slightly different jobs, and both were excellent at what they did. What makes the P-47's engineering truly remarkable, truly insane in the best possible sense, is that it defied conventional wisdom and yet worked brilliantly. Kartveli and his team looked at everyone who said a fighter needed to be light and agile, that a large radial engine was unsuitable for high speed, that turbocharging was too complex for fighter applications, and they essentially said, let's try anyway. And then they made it work through meticulous engineering and obsessive attention to detail. Today, when you visit aviation museums around the world, you'll often find P-47 Thunderbolts on display. A few still fly, maintained by dedicated collectors and preservation organizations. When you stand next to one of these giants, when you truly absorb the size, the visual weight, the complexity visible even from the outside, you begin to understand what made this machine so special. You can trace the lines of the air ducts from the fuselage intakes to the rear where the turbocharger sits. You can see how thick the wing is, how it needed to be to hold all that weaponry and fuel. You can look at the engine and simply be struck by its commanding physical presence. And if you're lucky enough to see one in flight, to hear that engine roar, to see the aircraft roll and dive with surprising agility despite all that weight, you understand viscerally why pilots loved, or at least deeply respected, this aircraft The history of engineering is full of compromises, of elegant solutions that do more with less. And there is certainly beauty in that approach. But there is also a different beauty, a kind of raw glory in doing more with more. The P-47 Thunderbolt was this approach personified. It was intentional excess. It was unapologetic power. It was the conscious decision that when lives were at stake, when wars were being fought, you didn't cut corners. You didn't make unnecessary compromises. The men who designed the P-47 didn't live to see the modern era of aviation with its supersonic jet fighters, variable geometry wings, fly-by-wire control systems, and beyond visual sight capabilities. But the principles they applied still resonate. The idea that you design for the worst-case scenario and then add margin. The idea that ruggedness has tactical value. The idea that complex systems can be reliable if they're engineered correctly. And perhaps most importantly, the P-47 teaches us something about the nature of innovation itself. Innovation isn't always about finding the most elegant or obvious solution. Sometimes it's about having the courage to pursue a vision that others consider impractical. It's about solving problems that others say are unsolvable. It's about proving that the impossible is merely improbable. Alexander Kartveli passed away in 1974, long after his most famous creation had been retired from active military service. But he lived to see the P-47 recognized as one of the greatest aircraft in history. He saw pilots who had flown the Thunderbolt in combat return decades later and thank him for building something that had brought them home. He saw his aircraft in museums, preserved for future generations to marvel at. There aren't many engineers who can say they created something that saved thousands of lives, changed the course of history, and pushed the boundaries of what was considered possible. Kartveli and the Republic Aviation team did just that. The P-47 Thunderbolt was their masterpiece, their lasting legacy, their contribution to human history. Looking back from the perspective of 80 years, it's easy to romanticize World War II, turning it into stories of clearly defined heroes and villains. The reality, of course, was infinitely more complex, dirtier, and more morally ambiguous. But what can't be denied is that extraordinary technological innovation was being driven by urgent necessity. And the P-47 Thunderbolt stands as one of the finest examples of this innovation. It was an aircraft born of necessity, refined through testing and combat, proven through thousands of missions under the most extreme conditions possible. It wasn't perfect. No complex machine ever is. But it was remarkable, it was effective, and it was a testament to what can be achieved when brilliant engineers are free to pursue unconventional solutions. The engineering madness of the P-47 wasn't in doing something absurd or impractical. It was in having the audacity to reject accepted limitations, to question fundamental assumptions, to build something that was simultaneously more complex and more capable than anyone had expected possible. It was madness in the sense that it was radically different, unexpectedly effective, and fundamentally transformative. And so, when we ask why the P-47 Thunderbolt's engineering was so insane, the answer comes in layers. It was insane because it defied conventional logic about fighter weight and design. It was insane because it implemented systems of unprecedented complexity in a combat application. It was insane because it worked brilliantly despite all the reasons why it shouldn't. And it was insane because it represented a vision that refused to accept limitations, that constantly pushed the boundaries of what was possible. Today, aeronautical engineers study the P-47 not as a historical curiosity, but as a case study in audacious design. Professors use it as an example of how to solve complex problems through unconventional approaches. Historians recognize it as one of the critical machines that helped win World War II. And aviation enthusiasts simply admire it as one of the most impressive aircraft ever, built out the roar of the Pratt & Whitney. SAR 2800 double WASP engine is no longer heard in the skies in large numbers. The days of massive formations of Thunderbolts darkening the sky over Europe or the Pacific are long gone. But the legacy remains. It lives on in every robust design principle applied to modern aircraft. It lives on in every redundant system that saves lives when the primary fails. It lives on in the collective memory of a generation that saw these machines in action and never forgot. The history of human engineering is punctuated by moments where everything comes together, where necessity, opportunity, and genius converge to create something truly extraordinary. The P-47 Thunderbolt was one of those moments. It was a machine that shouldn't have worked so well, but it did. It was a design that broke established rules, but established new ones. It was an aircraft that was too heavy, too complex, too expensive, and yet was exactly what was needed, exactly when it was needed. And perhaps that's what makes the P-47 story so fascinating and enduring. It's not just a story about metal and engines, about wings and guns. It's a story about vision and courage, about persisting when others doubt, about turning the theoretical impossible into practical reality. It's a story about what humans can achieve when the stakes are highest and the challenges seem insurmountable. The P-47 Thunderbolt stands as a testament to the human capacity to innovate under pressure, to create extraordinary solutions to seemingly impossible problems. And we must thank the Lord God for granting wisdom and insight to the engineers who dedicated their lives to creating this remarkable machine, an aircraft that not only changed the course of war, but saved countless lives and brought hope in times of darkness. May we always remember that behind every great achievement of human engineering lies not only talent and dedication, but also a divine blessing that empowers us to overcome the impossible.